Okay, hello. Welcome to Python Challenge for All. Okay, let's continue our work about perfect numbers. Okay, so last time we did, um, yes, we implemented the faster algorithm divs2, which uses the idea of usually the divisors come in pairs, okay, 1 and 4, 24, 2 and 12, such something like that. By doing that, we saw that, let's see the code. So here, um, the first naive implementation was up to 20,000. It took 14 seconds. Well, the second one took only zero point 0.3 seconds. So it's a big difference. So the homework was measure time and plot to compare. Did you try this? Okay, let's do it together. So to measure and compare divs and divs2, we need to measure for multiple sizes of the problem and draw a graph to visualize for visualization. So let's do that. Okay, to do that, maybe we can try to so up to u time. Okay, u limit, upper limit list equals, okay, say as um, 1000, okay, 1000, okay, this is not so. 1000, 2000, 5000, 8000, say 10,000, and 20,000. Maybe this is large enough, okay? 10,000 and 20,000. And for each, we'll time 1L initialized as empty list and do the list loop, okay? Upper limit in upper limit list, okay? So as usual, as last time, start time equaled time dot time. And for, yeah, just like this one, okay? For, say, k in range 1, 2, upper limit plus 1. This is not a big deal, but anyway. Um, so do the same thing, okay? Let's copy this and put it here so we can do it. Okay, yeah, so we can have it here. So for k up to ulim plus 1, sum of div1, divs equal 2 times k, print k. Now, we don't need print k, actually. Okay, we need print k. And e time is s time, okay, and print. And for up to n, ulim, okay, we write ulim time is sec. Okay, I think this works for, okay, at the same time, after doing that, maybe we need to put time 1L append e time, elapsed time. Okay? And at the same time, we write it down. I think this is good enough. Let's start it. Okay? So we'll do it again and again, but it takes taking time. In the meantime, we'll make another box to do nearly the same thing for um, the second algorithm. Okay, copy here, and instead of time 1, we put it into time 2, Instead of using divs, we use divs 2. And instead of putting it to time 1, put it into time 2. Okay? Oh, it seems we finished that. Up to 20,000 as last time, it takes 14 seconds. Okay, do the same thing for the algorithm too. Okay? Oh, it's quite fast, 0.16 second up to 20,000. Maybe we can do uh, much longer. By the way, we check that the answer is same. Okay? So now we'll draw graphs to compare. Plot using matplotlib. So for do that, what we need is, as usual, um, do the same thing. Okay? Import matplotlib dot pyplot as PLT. This is kind of a conventional way. So the easiest way is PLT plot ulim list. This is for x-axis, and time 1L. This is for y-axis. Okay? The first graph. Let's write it in a same graph to compare. Instead of time 1, we write time 2. Okay? And plt.show. This is all. Right, easy, right? So let's draw a graph. Okay, so interesting. Time 2 is almost 0. Time 1 grows up. Okay, this way. Maybe it's logarithmic. We can write, as usual, plt dot, let's see, y scale, both x scale, log, and also y scale log. Because both are kind of logarithmic, exponential, I mean. So let's take a look at it. This is more interesting. So both are linear in logarithmic scale, meaning that they are exponential. Okay? This is an interesting way to compare. Of course, you can use only one side if you want and see um, the difference. If you use this way, that will be like this. Okay, but anyway, the point is, yeah, they are straight line, linear in logarithmic scale. So let's see why div2 faster. The point is, it only checks the first half of the divisor range. Actually, it's not half. The point is, it's not half. Only square root, up to square root of n, rather than the original div 1, the original divs, okay, is check up to n, while div 2 check only up to root n, square root of n, okay? For 24 or 36 n, that's not big difference. But yeah, so time firm number drops from O. Do you know this? O, this is Landau's O to express the computational complexity. Okay, the first algorithm is O of n, while the second algorithm is O of square root of n, and it's much difference, big difference. Okay, for n equals 10,000, square root of n is 100, so the first one, the second one, the ratio is only 1%. Okay? For larger m, for million, n equals 1 million, square root of n is 1,000. So the ratio is 1 to 1,000. So the difference is much larger for bigger n. Okay? So let's see. For For 2, maybe we can try much bigger range. we can go to, say, much bigger range if you want, up to say 10 million or even 100 million. And you can predict how long it will take by looking at this graph. But it's one thing you should try yourself. Okay, so there are many interesting things about this result. But anyway, the point is, perfect number is an interesting topic. So I will let you know several perfect number trivia. So if you go to perfect number Wikipedia page, for example, you can find many interesting things about perfect number. So perfect number, a positive integer that is equal to the sum of its positive proper integer, proper divisors. Okay, proper meaning that excluding the number itself. Okay, they're also called aliquot sum. So perfect sum is defined as a number where it's equal to its aliquot sum. Anyway, the first four, okay, these four, okay, 6, 28, 4, 96, 81, 28. These were known from ancient times, okay? They were known since antiquity. But next one is much, much difficult to find. Yeah, there's a big gap between the, okay, six, yeah, these four. And next one is this. This is big. 33,550,336. Okay, 8 digits. And this is much larger. Okay, this is like 8 billion. No, 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 8 trillion. Okay, sorry, this is medium. 8 trillion and 137 billion. Okay, 8 billion, 137 billion. So the next ones are much larger. Okay, so it was only 15th century that were discovered after say 2000 years. Okay, another interesting story is that in 1876, Edouard Lucas, a French mathematician, found the 12th perfect number, which consists, which is made up of 77 digits by, hey, hand calculation. Great. This is known to be the largest one found by hand calculation. Okay? As of today, actually, only 52 are known. The total count is unknown. So there's a big challenge for human being to find more perfect numbers. Yeah, with a history of 3,000 or 4,000 mathematics history, only 52 are known. Okay? Here is page about that. The work is still going on with using computers. Okay. Uh, yeah, the theory about this is using use of Mersenne primes. Okay, there's an interesting story about Mersenne primes here. And now this GIMPS project is going on. Okay, Great Internet Mersenne prime search is going on to find the 53, the 53rd one. Okay, you can look here to see all the efforts we've made, the people have made. And 53, 52 was found several months ago. Okay. So that's all for today. Of course, yeah, you can read more about perfect numbers and Mersenne numbers and GIMPS project. Okay, I hope you will read that and like enjoy the mathematics story or try yourself. Okay, that's all for today. Come back next time. Bye bye.